Hello, y'all. Welcome to lesson 111 of my DP chemistry curriculum. Today we're going over reactivity 3.2.8. We're going to talk about electrolytic cell as an electrochemical cell that converts electrical energy to chemical energy by bringing about non-spontaneous reactions. We'll explain how current is conducted in an electrolytic cell, and we'll deduce the products of electrolysis of a molten salt. We'll be able to draw electrolytic cells as well and deduce each aspect of it. So when we look at electrolytic cells, we look at where they're used. So one of the common places is that when we take elemental metals, so elemental metals are often found as ores. And in that state, they are in ionic salts. So as an ionic salt, the problem is we want metal atoms. So how do we go from ionic salts to metal atoms? Well, what we need to do is some electron transfer. And the problem is metals tend to like to lose electrons, and in the ionic salts, they are cations already. They've lost their electrons. So how do we shove those electrons back in? So that's where we bring in electrolytic cells. Within the electrolytic cell, we use electric current to reverse a redox reaction. Or not necessarily reverse a redox reaction, that may not be the right way to say it, to instead to drive a non-spontaneous redox reaction. So how do we push that reaction forward? The truth is we use electricity. Now, to do this, we're going to use an example. So the example I'm going to pretty much use for the rest of this unit is aluminum oxide, Al2O3. It's where we get most of our aluminum from. We call it alumina. And basically, when I say alumina, I'm referring to the ionic salt of aluminum and oxygen. So the main reaction that we want to do is take Al2O3 and we want to get Al solid. That's how we produce our aluminum for stuff, but the issue is it's not that easy. The redox reaction we'll take is we take our Al2O3 and we melt it down into a liquid state. We react it with carbon in a solid state, and we'll produce aluminum liquid, which of course can just be cooled because it'll be molten, plus 3CO2. I'm getting ahead of myself with the coefficients as this reaction follows. So this is a reaction we're actually trying to push. We take our aluminum oxide liquid state, so molten alumina, and we're going to reduce it using carbon to produce our aluminum. So molten alumina is reduced with graphite to produce aluminum metal. And again, that'll be molten in the liquid state, seen here in our products, but we let it cool down and then we have our solid aluminum. So this process must happen via electrolysis. So what is needed in electrolysis? Well, all electrolysis consists of four things. One, we have a single container. So unlike a voltaic cell, which happens in two half cells, this happens in one big batch. We have two inert electrodes. Our electrodes we don't want to react. Now, in the alumina example, our electrode does react with oxygen because our electrodes are usually graphite or platinum. Now, we don't use platinum too often, mostly because it's expensive. In a school setting, we're likely going to just use a graphite rod. Second to last, we need a solution. This will be our electrolyte, and that will usually be our molten salt. And then lastly, we need a power source. Usually we use like a battery or some DC power source. When I say DC, I mean direct current. We don't want to use alternating current. Now, why are we going to melt our aluminum? Well, we have to use molten ionic salts so charge can move. When we learned about ionic structures earlier, we learned way back that ionic compounds cannot conduct electricity as there's no movement of ions. But if we melt it down, it moves. And so our molten ionic salt is going to be acting as our electrolyte. So both it is what we are doing electrolysis on, which is the process, and it is our electrolyte. So one other thing that we're going to do is usually we have to use a lot of heat, to melt salts. So often we usually might throw in additives. Some have additives to reduce melting point. It's much easier to do electrolysis on a 1000 degrees Celsius solution than a 2000 degrees Celsius solution. We get a lot less problems the lower temperature we are allowed to go. So if we can add some things that won't reduce or won't oxidize and will just be mostly inert, that is preferable. Those electrodes, as we mentioned before, they must be inert just so that they're not interfering with our redox reaction. So let's go back to our aluminum oxide example. So for aluminum oxide, Al2O3, our aluminum is what's going to be reduced, and our oxygen is what's going to be oxidized. So remembering our acronym red cat, at our cathode, that's our aluminum reaction. We're going to take Al3 plus ions. We are going to add 3 electrons to them, and they'll turn into aluminum. And again, this is all liquid. At our anode and ox, we're going to have our oxidization reaction. And there we're going to take O2 minus ions, and those are going to be converted into 1/2 O2 gas, and we're going to get 2 electrons. So these are the 2 reactions that will take place within our electrolysis. So just to be clear, though, we did say carbon dioxide was a product. So what's going to happen is that this is a very reactive oxygen, and it will react with graphite to produce CO2. What this means is that our graphite electrode isn't actually inert in this reaction. And what eventually happens is the graphite will need to be replaced. It actually gets reacted all the way through, and we lose it to the gaseous carbon dioxide. So we do have to replace the lead or the electrode at the anode quite often in this alumina electrolysis. So the last thing we're going to do here is just draw an example of our redox reaction. So in our electrochemical cell here, we will have sitting at the bottom a layer of aluminum that just stays and forms. And above that, we're going to have our molten aluminum oxide. So we'll go ahead and label these. This is the aluminum. It'll still be liquid, but as it gets deposited off the cathode, it will fall to the bottom, being more dense. This is going to be our Al2O3 in the liquid state. And within this, I'm just going to scooch this whole thing down to its own page. We're going to connect this thing to a power source. Now, in this diagram of power source, this is our power source. The large end represents the positive side, the small end represents the negative side, like a battery. And because this is our positive to negative side, we can guess that the flow of electrons are as such. Electrons move into the positive and away from the negative. So following this, we can figure out which side of our electrochemical cell, our electrolytic cell, is going to be our cathode and anode just from the diagram. Electrons are going to flow into here, and if those electrons are flowing in, it's going to charge this negatively. Therefore, our aluminum 3 plus are going to be attracted to it, and once they get attracted to that electrode, they will then deposit off the aluminum metal as they gain those electrons as they are reduced. Furthermore, as electrons are leaving, where are those electrons coming from? Well, they're coming from the oxygen. O2 minus is going to interact with this electrode. 2 electrons are going to leave, moving straight up, while 3 electrons came down. And coming off it is going to be our O2 gas, which, again, this will react to form CO2. So I'll just throw a little C in there. And this is our electrolytic cell. Now, we can remember that because aluminum is being reduced, we know that the right side is our cathode and the left side is our anode. So you should be able to recognize electrolytic cells from galvanic cells or voltaic cells. And furthermore, you should be able to recognize what is being produced at each end. Given any combination of ionic salts and such, you should be able to predict the products of an electrolytic cell, as well as the cathode, the anode, and draw this entire diagram. Hopefully this helps you understand these a little bit more, and have a great day.